Hello everyone, this is Patrick Dills from the Reach Lab at the University of Wisconsin-Madison. And in this talk, we're going to focus on some recent work where we explored the use of hybrid actuation in kinesthetic handheld haptic interfaces. So the ideal handheld haptic actuator would address all the components of dynamic range, including force, magnitude, bandwidth, and transparency, while being compact and lightweight. Conventional haptic actuators, which are summarized in the table above, have been shown to address only a subset of dynamic range, and they fall short from the ideal actuator. Hybrid actuators, defined in this context as the combination of active energy supplying actuators, like a DC motor, and passive energy absorbing actuators, like a particle brake, have the potential to improve handheld haptic devices. Hybrid actuators have been used in grounding kinesthetic haptic devices, and they've been shown to increase the stable range of impedances, the actuator torque density, the force rendering capability, and the energy efficiency of the actuators. So one might ask why hybrid actuators are not more widely used. And why haven't they been used in handheld and mobile devices? And really the answer is they're complicated. Hybrid actuators sometimes employ mechanical solutions with multiple brakes, clutches, and differentials to make control easier and to mitigate passive actuator nonlinearities. Current control solutions for hybrid actuators often avoid hard nonlinearities in passive actuators by eliminating zero velocity torque, resulting in reduced dynamic range and actuator capability. Our research is focused on a control approach which compensates for passive actuator nonlinear effects while achieving a higher dynamic range. The control approach allows for a simple parallel connection between active and passive actuators. Our control approach uses passive actuator torque feedback and a new torque partitioning method, allowing the active and passive actuators to work together more closely. Torque partitioning uses two methods, which we're calling model-based passive partitioning and stiffness-based passive partitioning. Model-based passive partitioning relies on a particle brake model, which predicts brake torque output and allows us to remove undesirable brake commands which oppose the torque command. Stiffness-based passive partitioning controls the output of the passive actuator and transitions the entire actuator between active-only rendering at low stiffness and hybrid rendering at high stiffness, ensuring the virtual stiffness is rendered accurately. And we experimentally showed that our hybrid actuator and control system can achieve a virtual stiffness of as much as 60 newtons per millimeter at the output, double that of the active actuator alone. Impedance frequency responses show that the hybrid actuator can render a wide range of stiffness over a wide frequency range as high as 100 Hz, and you can really feel the difference when rendering common virtual environments like this button force profile, which includes a high frequency click along with regions of transparency, low stiffness, and high stiffness. We think that with hybrid actuation, it's possible to reach a new level of performance in handheld haptics, where each component of dynamic range is addressed.